let's say I have 3 over 2 times the cubed root of x plus the cubed root of 5. So now I've changed things, right? Up until this point, we've only had monomials in the denominator when we've changed the index. Right. So now I have a binomial, and if I notice, I have cubed roots, right? They're not square roots, they're cubed roots. So when they were square roots, we were trying to do the a plus b, a minus b, right, to get a squared minus b squared. Well, now what we want to do is use the sum or difference of cubes. So we're going to say because it is a binomial with cubed root, use sum or difference of cubes. So let's just recap the sum or difference of cubes. So let's talk about the sum of cubes. The sum of cubes tells us if I multiply a plus b times a squared minus ab plus b squared, we end up with a cubed plus b cubed. The difference of cubes tells us if I have a minus b and I multiply that by a squared plus ab plus b squared, we end up with a cubed minus b cubed. And ultimately, we want the a cubed plus b cubed or the a cubed minus b cubed because that's what will get rid of the radical, right? If I have the cubed root raised to the third power, the radicals cancel out with the exponent. So here we have, let's rewrite it again, we have 3 over 2 times the cubed root of x plus the cubed root of 5. So I'm going to consider this a plus b. So the 2 cubed root of x is my a, the cubed root of 5 is the b. So if I have a plus b, I'm going to multiply that by a squared minus ab plus b squared. And in this scenario, my a is 2 times the cubed root of x, and my b is the cubed root of 5. So I'm going to take this binomial and I'm going to multiply it by the trinomial a squared. Well, if I'm going to take 2 cubed root of x and I'm going to square it, that means we're going to take 2 cubed root of x times 2 cubed root of x, which is going to give us 4 cubed root of x squared. So we're going to multiply it by 4 cubed root of x squared minus ab. So now I'm going to take my a and my b and multiply them. So this is going to be 2 times the cubed root of 5x plus b squared. So now cubed root of 5 times cubed root of 5 is going to be the cubed root of 25. So this is the equivalent of my a squared minus my ab plus b squared. I multiply it on the denominator and I also multiply it in the numerator. And now my denominator my denominator is going to give us a cubed plus b cubed. So let's cube them. My a cubed is going to be 2 times the cubed root of x raised to the third power. So the 2 gets raised to the third power, and the cubed root of x gets raised to the third power. Well, 2 raised to the third power is 8. What's the cubed root of x raised to the third power? Just x. Good. Just x. So now we're going to have 8x. And now I'm going to take my b and raise it to the third power. And when we take the cubed root of 5, raised it to the third power, we're just going to get 5. And in my numerator, I can just leave it as 3 times the quantity of the cubed root of x squared minus 2 times the cubed root of 5x plus the cubed root of 25. If you wanted to distribute in that 3, could you? Absolutely. Okay, so to sum this up, if a denominator has 2 terms, what do I mean when I say 2 terms? What is it? A binomial. So when if a denominator has 2 terms, a binomial, and at least one of the terms involves a cubed root, then the factors of a cubed plus minus b cubed, which we call the sum or difference of cubes, can be used to rationalize the denominator. Okay, you guys try this one. So here you have a minus b. So what are we going to multiply by? A squared plus ab plus b squared. And that should give us a cubed minus b cubed. So we're working with the difference of cubes now. Last time it was the sum of cubes. Who thinks they have an answer for me? You, Philip?
2 times the quantity 4 cube root x squared plus 2 cube root 3x plus cube root 9 over 8x minus 3.
There's so much about what Philip said that I love. I love that he declared everything as the cubed root. He didn't just say radical, he didn't just say root, because when it's just a radical, you're not describing the index. When you say root, we're implying a square root. So I love that he said the cubed root of 3. I love that he said the quantity, 2 times the quantity of. I like so much of what he said. If you distributed that in, are you still good? Absolutely. Anybody need to see me do this? Okay, let's move on to today's lesson. So we are not going to finish today's lesson. It's a long one. We'll start it and then we'll finish it up, I guess, on Thursday.
Does that mean we'll have no homework tonight?
No homework tonight. Yes?
When's the test for you?
I did work that out yesterday. I believe we should be on track to have the test. You guys are period 1. Monday next week. Yeah, I think so. Review Friday. So that's our projected test day, Monday. You drop Tuesday, yeah. Okay, let's go through this. So our new lesson, so we are Unit 6, Day 4. We're going to talk about rational number exponents. Okay, let's say I have x to the half power times x to the half power. What are the rules for multiplying variables? You keep your base and do what? Add the exponents, right? You keep your base, you add the exponents. So I'm going to keep my base of x, and when I add my exponents, what's a half plus a half? 1 whole, right? In the world of radicals, when I multiply or square roots, I should say, in the world of square roots, when I multiply what two together, will it just give me the radicand or the base of whatever it was? When you multiply a radical times itself, or a square root times itself, right? So if I had the root of x times the root of x, wouldn't that give me x to the first? What does this tell us? This tells us that exponential and radicals are very similar, and they're actually interchangeable. Exponential and radicals are interchangeable. What does that mean? Well, do we agree this has an index of 2 and this has an exponent of 1? And this has an index of 2 and this has an exponent of 1? So this tells me that x to the half is equivalent to the square root of x to the first. And this doesn't only work for square roots. It actually works for any index, that you can change any radical with any index into a base with an exponent. So how do we do it? How do we go from exponential to radical and radical to exponential? The rule is going to be if I have the nth root of a to the m power, that's the equivalent of a to the m over n. So the index becomes the denominator, the exponent is the numerator. And you could go either way. You could change exponential to radical or radical to exponential. And you'll see when I'm doing problems, I'll start flipping between them to see what's easier. Okay, now we have to know the rules. So when I say write something in exponential, that means write it with an exponent. So if I say change the root of 2 into exponential, that's going to be 2 to the half. How did I know it's 2 to the half? There's no index here. But when there's no index, what's it implied? That there is a 2. And do we agree this really had an exponent of 1? It's really 2 to the first? Okay, let's say I want us to change the fifth root of x squared to exponential. How am I going to change the fifth root of x squared to exponential? Well, my radicand becomes my base. Is that index my numerator or my denominator of my exponent? The denominator. So it's going to be x raised to the 2/5 power. All right, and then sometimes I'll say write it in radical form. So let's say I have 3 to the 2/3 power, and I want to write this in radical form. Well, this is going to be the cubed root of 3 squared. But what's 3 squared? 9. So this is going to be the cubed root of 9. All right, so for this next part, I want us to convert to rational exponents. All right, so if I have the fifth root of x to the 4th, you tell me, how would I write that in exponential form? Noah? You got it, x to the 4/5. Now I'm going to have the fifth root of 4x squared. Now we can look at this as 4x squared raised to the 1/5 power, or this could be looked at as 4 to the 1/5 x to the, what do you think? 2/5. Right, just distributing that 1/5 exponent. Are we taking the 4th root of 7? No. So this is just 7, then a raised to the 1/4. That 1/4 is only on the a. It's not going to the 7. How does that differ from this? Is this 4th root going to the 7 and the a this time? Yeah, so we could look at it as 7a raised to the 1/4, or what is it? 7 to the 1/4, a to the 1/4. Okay, now let's practice writing in radical form. Who has that exponent of 1/3? The 5, the y, or the 5 and the y? Tori? Just the y. So now the 5 is just our whole number, and the radical only goes over the y. So we know we're going to have our radical. Y is going on the inside. The denominator is our index, so this is the cubed root of y to the 1st. Do I need that 1 on top of the y as an exponent? No. Is it okay if you put it? Sure. Okay, what about this? Is everything under the radical this time? Yeah, so we're going to have the cubed root of 5y. Okay, you guys do this one. Tell me, what do you get? Anybody? What do we get? Danny?
It's like the 7th of the radical y cubed.
Yep, the 7th root of y cubed. Okay, let's say I have x to the 2/5, y to the 1/5. First thing I'm looking at is their denominator. Can somebody tell me, why am I first looking at their denominator? Please? Good, because I have to see if I could put them under the same root. Is their index the same? Yes, so can I put them under the same root? Absolutely. So this is going to be the 5th root of x to the 2nd y. Now let's see what happens when they don't have the same index. So this is really the biggest advantage of using exponential versus radical. Because right now, if I had the 5th root of x times the square root of y, there is nothing we can do with it in radical form. There's nothing we can do with it in radical form. It's a different index. I cannot multiply. But in exponential, their exponents are written as fractions. And can't a fraction be written in multiple ways but still have the same value? Absolutely. So what I'm going to do to be able to put them under the same radical is I'm going to create a common denominator. And what's a common denominator of 5 and 2? 10. So this is going to be x to the 2/10 times y to the 5/10. Now, do they have the same index? Absolutely. So this is going to be the 10th root of x to the second, y to the 5th. Okay, you guys try this one. All right, tell me, what did you get? What did you get in radical form? You got it, the 6th root of x squared y. Anybody need to see me do it? Okay, let's say I have a numerical base. Let's say I have 81 raised to, actually, do this one. 27 raised to the negative 5/3 power, and I want positive 5/3 power. Let's do this first. Positive 5/3 power. Okay, if I want to simplify this, I'm actually going to do a little bit of manipulation. I'm going to look at the denominator here, and I'm going to ask myself, okay, is there a base I can change 27 to, that I can take that base and raise it to the 3rd power? That will give me 27. Is there any base that I raise to the 3rd power that can give me 27? Pages? 3. So that's what I'm going to do. I'm going to take this 27 and I'm going to change it to a base of 3 raised to the 3rd power. Can someone tell me why I chose to do that? Why did I look at the index and try to change this to a base raised to that? So yeah?
Because you wouldn't want to raise 27 to.
True, you're right. So it's like a key to it helps with simplifying. But why did I specifically try to change it to something raised to the 3rd power? Like, why didn't I try to change it something raised to like the 2nd power? The index is 3. Okay, I need more.
Because when you distribute the 5/3 in, the 3's cancel out.
Exactly, because when you have a power raised to a power, don't you multiply? And then ultimately, won't those just cancel? And that's how I chose the 3, because I wanted that denominator to cancel. So this is going to be 3 to the 3rd raised to the 5th. Well, power to a power, you multiply, those 3's cancel. So we're just left with 3 to the 5th power. And when we have 3 to the 5th power, it's going to be 3 times 3 times 3 times 3 times 3, right? 3 times 3 is 9. 3 times 3 is 9, another 9 times 3. So then you have 81 times 3, which is 243. Okay, let's try this next one. I want us to simplify 81 to the 3/4 power. And I want us to simplify this. So where is my brain going here if I want to simplify this? I want to change that base. What do I want to change that base to? Good. Something raised to the 4th power. Why? Why do I want it something raised to the 4th power? So this denominator will cancel. That's why. So we know 3 to the 4th power is 81. So now I have 3 to the 4th power raised to the 3/4 power. And then what happens with the 4s? They cancel. So now I'm just left with 3 to the 3rd power, which is going to be 27. Okay, next one. I want us back to change to radical. So now I have x raised to the negative 2/3. What does the negative mean? All it means is I'm moving it where? To the denominator, right? So this is the equivalent of 1 over x to the 2/3. Well, isn't this the same as 1 over the cubed root of x squared? Can I leave it like this? Can I leave it like this? No. What do I have to multiply to get the radical to cancel? Kai?
4 cube root 4. Wait, oh, my bad. I wrote the equation down wrong. Cube root x squared.
X squared?
X.
X, you got it. Why cubed root x? Because I need to create a triplet, right? I need 3 x's. I already have 2. I just need 1 more. So then this is going to give us the cubed root of x over x. All right, so what's going on here? This is going to be the 4th root of y to the 3rd over the 4th root of x squared.
Can we not simplify 2/4?
You can, then you'll have a half, right? But then you're going to multiply it by up here, and then you're going to have to change it back to the 4th. Okay, so you tell me, what do I need to multiply this time to rationalize? Not Tori, somebody else, not Noah either. James?
X squared, like the root of x squared.
What? Say it one more time.
The root of x squared.
Just the root of x squared?
Oh, with the 4.
You got it. 4th root of x squared. So in our denominator, we're going to be just x, right? We're going to have a group of 4 x's, so that's just x. And in our numerator, we're going to have the 4th root of x squared y cubed. Okay, let's talk about the rule for multiplying exponents. Do we agree if I have x to the a times x to the b, we end up with x to the a plus b power? So if I have 5 to the 3/8 times 5 to the negative 1/8 times 5 to the 2/8. first thing I'm looking at is our base. Are all our bases the same? Yes. So the rule says keep our base. Do we multiply 5 times 5 times 5 and get 125? No, 5 is not a coefficient. 5 is the base. So you're going to keep your base. So I'm going to keep my base of 5. And then what am I doing with my exponents? I'm adding them. 3 minus 1 is 2. 2 plus 2 is 4. So now I have 5 to the 4/8. But what can I do with the 4/8? What can I do with the 4/8? We can simplify it down to a half. And then if I'm writing 5 to the half as a radical, what is that going to be? Root 5. So I will tell you on the test, I will want all answers, final answers in radical format. All final answers will be in radical format, but that doesn't mean you're not going to have to work with the exponential. You're going to sort of have to flip-flop throughout your problem, but your final answer will be in radical. So, Tori?
Is it the most simplified form in radical form, or is it either one?
The most simplified form?
Like if it asks you just to simplify something,
I would have. So if it just said simplify, then you could have left it as 5 to the half or root 5. But I'm going to be specific. I'm going to write on the top of the test, all final answers must be in radical form. So you might be thinking, okay, well then this whole lesson is pointless and I don't need to pay attention. No, that's wrong, because then I could give you something like this. And I cannot multiply this in radical form. So I'm going to have to change it to exponential. So even though my final answer has to be in radical, I have to use exponential within the problem. So I'm going to change this to exponential. This is x to the 1/5 times x to the half. You cannot multiply them if their indexes are different. So, since I can't multiply them if their indexes are different, now I'm in exponential. What am I going to create? A common denominator for their exponents. So this is going to be x to the 2/10 and x to the 5/10, which is going to give us x to the 7/10. And now if I'm going to write this in radical format, this is going to be the 10th root of x to the 7th. Okay, and now sometimes I even throw a little curveball at you. So here we have the 4th root of x to the 2nd. Oops, sorry, 4th root of x to the 3rd times the 5th root of x to the 2nd. Can I multiply these right now? No, we cannot multiply them right now. So what am I going to do? I'm going to change it into exponential. X to the 3/4 times x to the 2/5. I'm going to create a common denominator. What is my common denominator this time for my exponents? 20. So this is going to be x to the 15/20 power times x to the 8/5. And now when I multiply, I'm going to get x to the 23 over, oops, sorry, I said 8/5. This is 8/20. All right, 23/20. Some kind of red flag should be coming up. Any ideas? Patience?
It's greater than 20, so you would be able to plus it.
Excellent. Because my numerator is bigger than the denominator, that means my exponent on the inside is bigger than my index, which means can I create a group? Absolutely. So if you wanted to change it into radical to c, you'd have the 20th root of x to the 23rd. But you couldn't leave it like this. You would have to then recognize, okay, well, if I have x to the 23rd, I could create one group of 20 x's, which means I'm going to pull one x out, and I will have 3 x's left inside. Can I multiply these? How many people say yes, we can multiply them? How many people say no? Good, why no? Because it's different, their indexes are different, right? So what am I going to do? Change it to exponential. So this is 9 to the 1/3 times 3 to the half. Before I try to create a common denominator in their exponents, I can potentially make this even easier for myself. Because do we agree 9's a base and 3's a base? And the rule says if the base is the same, what can we do with the exponents? Add them. Well, can I change 9 into a base of 3? Absolutely. I could change 9 into the base of 3 if I change it into 3 raised to the 2nd power, and then that's raised to the 1/3 power. So this is going to be 3 raised to the 2/3 power times 3 to the 1/3 power, half power, sorry. Okay, now the rule says keep your base, add your exponents, but what do I realize? My denominators are different, so should I change them to the same denominator? Absolutely. So this is going to be 3 to the 4/6 times 3 to the 3/6, which is going to give us 3 to the 7/6. Again, what should be a red flag here? What should be the red flag? You guys aren't giving me much to work with today. Tori?
It's an improper fraction.
I'm sorry?
It's an improper fraction.
It is an improper fraction, which means what? We're going to have a group of 3's, right? So this is, if you want to change it to radical, this is going to be the 6th root of 3 to the 7th, which we're going to pull out a 3. So 3 times the 6th root of 3. How am I doing on time? Okay, one more and then we'll call it a day. One more and then we'll call it a day. Okay, so I'm not really sure what to do here, so I know I can't subtract them. So my plan is let's just go to exponential. So this would be 4 to the 1/4 minus 2 to the half. And I still cannot subtract these. So then I'm going to say, okay, well, can I at least try to create the same base? Can I change 4 into a base of 2? Absolutely. So we're going to have 2 to the 2nd raised to the 1/4 minus 2 to the half. So then this is going to be 2 raised to the 2/4 minus 2 to the half. But what's 2 to the 2/4? Isn't that a half? or sorry, what's 2/4? Isn't that a half? So then what I end up with is 2 to the half minus 2 to the half. Or you could look at it as root 2 minus root 2. Well, whenever you take something from itself, what's your difference? 0. All right, and that's where we will stop.